Good afternoon, everyone. My name is John Ashley. I'm a developer relationship manager with NVIDIA, focusing primarily on people porting to the IBM Power and GPU platform. I'll wait for them to start the countdown timer here, just giving people another second. I'm going to try and keep this very conversational. Feel free to stop me and ask questions. I promise to only read 2 slides and then just talk to the rest. So the first one I'm kind of almost going to read is this one. These are the things I want you to take away. So I thought I'd tell you these first, and then you'll know what you're listening for through the rest of the talk. If you are already up running on Power 8 and Tesla K80, which I hope you are, because it's a fantastic platform, then moving to Power 8 Plus and the new Tesla P100 is going to be really easy for you. And your code is going to be, we expect, at least 2 times faster. Probably 3, but at least 2. That's whether it's limited on the performance of the GPU or whether it's limited on the performance of data moving from the CPU to the GPU. If your code happens to be a deep learning code, it is going to be a lot more than 2 times faster. Depending on whether you can take advantage of some of the half precision, the FP16 instructions on Pascal, it could be an awful lot faster. There's also some things that are happening that aren't just performance, right? We are continually focusing on making adopting GPU-accelerated computing easier. And especially on power, we have some interesting tricks up our sleeve for that. So we've talked about in other forums here unified memory coming with CUDA 8. And that really will simplify the memory management process no matter what platform you're on with Pascal and CUDA 8. But it turns out OpenPOWER with Power 8 Plus and Pascal and EnvyLink is specially advantaged there because the higher bandwidth between the CPU and the GPU will automatically be taken advantage of by the unified memory technology. And so your code runs, and it was easy to get there, and by the way, it just runs faster on power. So these are key takeaways. That's I promise not to read any other slides. We're going to talk about, briefly, I'll touch on what's different about Pascal, the P100 product that we announced yesterday. I will talk a little bit more about EnvyLink and why we're so excited about that in general and especially in the context of OpenPOWER. We'll touch again on unified memory, and then I'll talk a little bit about resources and how you can get started on moving to Pascal, because hopefully by then, if we get there and I've done my job, you are going to be itching to get started to get your code up and running on Power 8 Plus with P100 and EnvyLink. So the P100, Jensen did a great job announcing it. Yesterday. I'm not going to try and outdo his presentation or his enthusiasm. I'm going to give you a couple of the numbers. But one of the key things here, and you can read them yourself, it's fast. It's at least twice as fast as our prior generation, except for the interconnect. In the interconnect, that EnvyLink interconnect is 5x the speed of the PCIe that we're using in our current generation products. And that's net. That's aggregated over each socket and each GPU, sees 5x more bandwidth. This is a huge step change. If you know where we've been going in Moore's Law, because the GPU is a parallel accelerator and has always been parallel, we've been able to ride Moore's Law pretty well, right? We haven't had some of the issues scaling that other architectures have had. But we haven't, so we've been able to scale flops pretty easily. But scaling memory bandwidth has been a challenge at that same rate, as has scaling the interconnect. And so as Jensen said yesterday, right, some miracles occurred. And not only did we get a huge step increase in the memory performance on P100 for its local memory subsystem, We also invested in NVILink technology to connect GPUs and GPUs. And in the OpenPOWER context, we can also add CPUs to that. IBM went and adopted NVLink into their chip family as well. So we have this capability and this performance, and one of the nice things about it is that internally, it looks a lot like our current generation Maxwell parts if you're a programmer. Performs a lot differently. It's much faster. It's got some extra instructions. It's got new bells and whistles. But in general, if your code runs well on Kepler or Maxwell today, it will translate very well, we believe, to the new Pascal architecture in the P100. The resources per core either stay the same or go up. Just the entire architecture, the look and feel of the chip from a code perspective is very similar. One of the differences is NVLink, and one of the things we didn't want to do was make that hard to use. So NVLink is transparent to the developer. From a hardware architect's perspective, it's not transparent at all. It's not PCIe. It's a separate electrical interconnect. It's a new thing. There's a lot of innovation, a lot of effort went into making that fast and energy efficient and scalable. And so as long as you have a hardware that supports it and a motherboard that's laid out to support it, it just runs faster. When you do a memory copy, when data gets moved through unified memory, it's just faster than it is over PCIe. There's no other coding change you have to make to get those benefits. That didn't work. Try again. So I mentioned that there is, right, the motherboard plays a part here. The NVLink interconnect is an electrical interconnect. It's got to be wired up. So there are a number of options for how to build systems. And one of the nice things about OpenPOWER is it's an innovation-friendly platform. And so I'm not going to announce any particular vendor's plans or configurations, but these are certainly configurations that are possible. Some of them are likely. There are more. You don't have to lay out these interconnections symmetrically. You can mix and match PCIe and NVLink, as we're doing in the DGX1 product we announced yesterday. But one of the unique things we can do with Power 8 is share that high-performance, high-speed connection. And if you look at something like this bottom option with 2 GPUs attached, each of those GPUs gets 80 gigabytes a second bidirectional bandwidth back to the CPU. This is system memory speed for an awful lot of mid-range systems today. This is an incredible amount of bandwidth for the CPU and the GPU to be able to share. And what that really does is that lets us get the right data onto the right part of the compute platform at the right time. This helps us help you fight Amdahl's law. You still can't get around that speed limit, but we can let you move things more easily to the right place to run it optimally. Yes? Oh, okay. So Amdahl's law says that if you have a code, and I'll paraphrase roughly, if you have a code that has some serial work and some parallel work, no matter how fast you speed up the parallel part, you will never get faster than the length of time of the serial part. So I have some work that I can accelerate, some that I can't. If 60%, if half my job is serial, I can't parallelize it, and half is parallelizable, no matter how fast I make the second half, I can't be more than twice as fast as I was at the start, unless I make the first half faster too. And NVIDIA's always recognized this, and this is a big deal for us. This is why we build a discrete GPU, and we team up with an appropriate CPU. And so Power 8's an exciting platform because for a lot of the data-centric challenges that are coming up, Power 8 is going to be a fantastic place to run that stuff that isn't well suited to the GPU. So if it's not good GPU problem crunching, number crunching, data manipulation, if it's not GPU friendly, chances are the best place to be running that is going to be on Power. And so we can quickly move the data there and run it. And then when it gets to a phase where it's GPU friendly again, we can quickly move it back. So this is really about teamwork, in a sense. Inside the server, and technologies like unified memory are really about making that teamwork more transparent to the developer. If you have code today that do explicit memory management, it'll keep working. And it's just going to run faster on NVLink because when you copy memory, it's just going to be faster. But if you don't have that code, if you want to start adopting some of these convenience features in programming, you could start now, right? Since CUDA 6 and with Kepler, we've had unified memory support. The hardware in Pascal does it better. It's got more features, more support. It lets you add some new features like over-allocating GPU memory for the first time. So you can actually declare more GPU memory than you have, and the CPU and the GPU will cooperate to move that data back and forth as it's needed. But the nice thing is that'll work anywhere. If your code has to run on multiple platforms, it's fine. It'll run everywhere. But it will run better on Power. Depending on the topology of your motherboard, it will be 2, 3, or 5x faster than it would be on a PCIe connected system. OpenACC is always an option, and I believe Doug Miles will be talking a little later about the plans around OpenACC coming to Power. So I won't steal his thunder, but it's going to be an interesting option as well for primarily for scientific codes, but for some other codes as well. And again, it can take advantage of EnvyLink. It takes advantage of all these things in a very transparent way to the programmer. So let's say you want to get started. If you're lucky, you have GPU code, it's already accelerated, and it's running on Power today. And you're in a very happy place because it's just going to run faster when you get these Power 8 Plus and Pascal systems. Right? The Power 8 side will be a little faster. The GPU side will be a little faster, or a lot faster, depending on exactly what it is, 2x, maybe more. And, of course, the data movement will be faster. It's good. If you have GPU-accelerated code and you're on x86 today, make the effort to move it to Power now. Go ahead, get a Power and Kepler system. Get a performance baseline. You can actually then do some quick projections based on even these performance numbers I've given you, and get a pretty good idea for what that performance is going to look like when you get a Power 8 Plus system with Pascal. And if your code's not accelerated today, think about why not. Is your problem really not suited for parallelism? There's no parallel work there? Don't port. But you can look at other codes, right? There's most industries, most fields of science, there's another code that does something similar, and many of them may be GPU accelerated, and that may give you the hints you need to accelerate your code or to figure out whether it makes sense for you in your position to try and accelerate your code. You can look at libraries. There's a lot more of them out all the time, and certainly you can contact IBM or NVIDIA, and we'd be glad to talk to you about accelerating things. As Sumit announced, there is a new IBM NVIDIA Accelerator Lab that we're opening up jointly. And that the contact details were on Sumit's slide earlier. Email Sumit if you want details on that, or go ahead and get me. There are a number of talks that have happened already or will be happening on various of these topics. Since everything at GTC tends to get recorded and put up online, even if it's already passed, you haven't missed it, you just have to wait a couple of weeks. And then it'll be there for you forever online.